Hello everyone, today we're going to explore the incredible world of pH meters. Have you ever thought about how we ensure the quality of the food we eat, the water we drink, or even the soil where our plants grow? It all comes down to measuring pH levels accurately. pH meters are essential tools in many industries, including environmental science, agriculture, food processing, and medical research. These devices help us measure the acidity or alkalinity of solutions, providing critical insights where pH levels matter the most. For example, in environmental monitoring, pH meters evaluate water quality, helping us keep our lakes and river clean. In agriculture, they optimize plant growth conditions by measuring soil pH, ensuring our crops thrive. In the food industry, pH meters guarantee product quality and safety, extending the shelf life of our favorite food. And in medical research, they assess the acidity of biological samples, aiding in groundbreaking studies. Let's take a quick journey through the history of page meters to understand their evolution and importance. In the early 20th century, the concept of measuring pH was first introduced. Initially, scientists used chemical indicators to estimate the acidity or alkalinity of a solution, but these methods were not very precise. In 1934, a significant breakthrough occurred when Arnold Beckman invented the glass electrode-based pH meter. This innovation provided a more accurate and reliable way to measure pH levels and revolutionized the field. By the 1950s, pH meters became widely used across various scientific fields. These early models required manual adjustment of potentiometers, which could be cumbersome but a big step forward. The 1980s saw the introduction of digital pH meters. This device significantly improved the efficiency and precision of pH measurements, making them easier to use and more reliable. In the 2000s, advancement in microfabrication technology led to the development of even more sophisticated pH sensors. This modern device offer high sensitivity and real-time data integration, further enhancing the utility. Today, pH meters are essential tools in various fields, from environmental monitoring and agriculture to food processing and medical research. The continuous innovation in pH meter technology ensures that we can measure pH levels accurately and efficiently in many different applications. Arnold Beckman revolutionized scientific research with his invention of the first electronic page method in 1934. This device provided precise acidity measurements, which were crucial for industries such as citrus processing. Beckman's innovation led to the founding of Beckman Instruments, a company that developed other critical scientific tools, including ultraviolet and infrared spectrophotometers.
A typical pH meter has three key parts: a pH-sensitive glass electrode, a reference electrode, and a voltmeter. When you place this electrode in a solution, an ion exchange process happens. H plus ion from the solution interact with the glass electrode, generating a small voltage. The voltmeter measures this voltage and show it as a pH value on a scale from 0 to 14. The reference electrode provides a stable reference point during this process. Higher voltage readings mean there's a higher concentration of H plus ion indicating a more acidic solution, lower pH value. Lower readings suggest few H plus ion and more OH minus ions indicating a more alkaline solution, higher pH value. This way, the pH meter accurately determines how acidic or alkaline the solution is based on the voltage created by this electrode. In a conventional pH meter, you will find both the glass and reference electrode separate from each other. The glass electrode is designed with a potassium chloride KCl solution and a silver wire that's coated with silver chloride AgCl immersed in it. This electrode uses a specially formulated glass that coated with silica and metal salt, making it very sensitive to the H plus ion concentrations around the tip of the bulb. On the other hand, the reference electrode has a different setup. At the bottom of the reference electrode tube, there is a mercury covered with a paste of mercury mercurous chloride. Above this paste, a potassium chloride solution is placed and a platinum wire seal in a hollow tube help make the electrical contact. This reference electrode is housed in a non-conductive glass or plastic pump that is in it affected by the sample solution. The reference column solution within it maintains a fixed concentration, providing a stable voltage necessary for the accurate pH measurement. Now, let's talk about the new generation of pH meter, which use combination electrode. This combination electrode integrates all necessary components into a single probe. The glass membrane is the part that measures the H plus ion concentration made from specialized glass that allow ion exchange with the sample solution. Inside the electrode, There's an internal electrode coated with the silver chloride serving as the internal reference. The internal solution within the electrode is typically a pH 7 buffer solution of potassium chloride KCl. The reference electrode, also coated with silver chloride, is included in this combination designed to provide a stable reference potential for accurate pH comparison. A ceramic diaphragm, known as a junction, allows ion exchange while keeping the internal and external solution electrically separated. Lastly, there's a filling hole used to refill the electrolyte reservoir, ensuring the electrode maintains its functionality over time. This integrated design simplifies the measurement process and enhances the accuracy and reliability of pH measurement.
The signal detection mechanism in a pH meter involves converting the chemical information related to the hydrogen ion concentration in a solution into an electrical signal. Here's a detailed explanation of the signal detection mechanism. First one is component of the pH meter, which is glass electrode. pH sensitive glass membrane. The tip of the glass electrode is made of a special glass that is selectively sensitive to hydrogen ion, H+. Internal solution. Inside the glass electrode is a solution of non-pH, typically a buffer solution with a constant concentration of H plus ion. Next is internal reference electrode. An electrode, often silver or silver chloride, immersed in the internal solution. For reference electrodes, we use reference junction, a stable reference half cell that maintains a constant potential, usually filled with a potassium chloride solution. Next is electrode housing. The reference electrode is often combined with the glass electrode in a single probe, but it can also be separate electrode. Next is signal generation and interaction with the solution. When the glass electrode is immersed in a solution, hydrogen ion from the solution interact with the pH-sensitive glass membrane. This interaction generates a potential voltage across the glass membrane due to the difference in hydrogen ion concentration between the internal solution and the external solution. For potential difference, the potential difference E across the glass membrane is a function of the hydrogen ion activity AH plus in the solution, and it's given by the next equation below. Number three, signal detection, a measurement of potential difference. The potential difference between the glass electrodes and the reference electrode is measured by the pH meters interval electronics. The potential difference is directly related to the pH of the solution according to the next equation. For temperature compensation, the temperature affects the potential difference and the sensitivity of the glass electrodes. Modern pH meter often includes automatic temperature compensation (ATC) to correct the pH reading based on the temperature of the solution. Lastly is signal processing. Analog to digital conversion. The analog voltage signal generated by the potential difference is converted into a digital signal by the pH meters analog to digital converter ADC. Next, for the display and the output, the digital signal is processed by the pH meter microprocessor, which calculates the value. The pH value is displayed on the meter screens, often with the option for recording or transmitting the data to other device. Oh, no, no.
So moving on to the comparison standard page meter and advanced page meter. The first features, which is type of electrode. Standard page meter is using AGAG electrode reference system, and advanced page meter using glass formulation with reduced alkalinity error and beta selectivity. The measurement type of standard page meter, it is using a sensitive galvanoscope by measuring voltage, while advanced pH meter, it is converting electrode voltage to pH by using microprocessor, which is the nanomaterials used in advanced pH meter. Next is calibration. Standard pH meters, it is a manual calibration, while advanced pH meter is automatic. The display for standard pH meter is analog dial display, while advanced pH meter is digital screen with multiple decimal places. The ease of use for um, Standard pH meter, it is required expertise to operate, while advanced pH meter, it is user friendly. So since advanced pH meter using nanomaterial, which is microprocessor, it is more expensive compared to the standard pH meter. And the additional features for advanced pH meter, it can store pH readings for multiple sample, while the standard pH meter, there is no additional features. Since advanced pH meter is nowadays being used by most industrial, there are several implications that we need to take look, which is the first one is versatility and integration. Modern pH meters now capable to connect with other laboratory equipment and automated system. It is allow comprehensive data logging, remote monitoring, and streamlined workflows to improve process efficiency. Second one is multi-parameter. Advanced pH meters now offer multiple parameters such as conductivity, dissolved oxygen, and temperature that can provide a more comprehensive understanding towards the sample characteristic. The third one is accuracy and reliability. The advanced pH meters equipped with features like temperature compensation, automatic calibration, and digital displays to provide more accurate, reliable pH measurement. It is crucial for pharmaceutical, food, and beverage, and also water treatment since it is required the precise pH control. Last but not least is durability. Developing pH meter that durable and resistant to the harsh environments can ensure the long-term reliability and reducing the need for frequent replacement. Thus, it can reduce the maintenance replacement costs that very important to the industrial and field application. Moving on to the pros and cons for pH meter. So for the pros, the pH meter is can improve the accuracy since it can offer incorporate features such as temperature, automated calibration, and digital displays that can provide more information that accurate towards the pH measurement. The second one is portability. pH meter that are durable and resistant to the harsh environments can ensure the long-term reliability for the pH meter. And the third one is versatility. It can capable to connect with other laboratory equipment that have automated system to allows the comprehensive data logging, remote monitoring to improve overall process efficiency. And last but not least, multi-parameter. pH advanced pH meter is nowadays equipped by the multiple parameters that can measure simultaneously can that provide more understanding of the sample characteristic. Next is the cons of pH meter. The advanced pH meter that have advanced features, it is more expensive in the market compared to the older and simpler models. It makes some users and organizations hard to afford because the limited budgets. The second one is complexity. Um, it is required technical expertise to operate and maintain since the advanced page meter has advanced technology such as nanomaterials that could be challenge for some users. The third one is potential fragility. More advanced pH meters will cause more complex construction that may lead to damage compared to the simple models. And last one is dependence on power and connectivity. Advanced pH meter required stable power source and network connectivity to utilize their features that make it not portable.
In conclusions, pH meters are indispensable tools for accurately measuring the acidity or alkalinity of solutions. They work based on the potential difference between a reference electrode and a pH-sensitive glass electrode. This potential difference generates electrical signals that the pH meters detects and convert into pH values, which are then displayed either digitally or on an analog scale. Technologically, advancements have significantly improved pH meters, making them more precise and user-friendly. Modern pH meters features digital displays, advanced sensors, and real data integration, allowing for more efficient and accurate measurements. These devices are crucial in various fields, where precise pH measurements are essential for quality control, research, and monitoring purposes. The continuous innovation in pH meter technology ensures that we can rely on these tools for accurate and reliable pH measurements across different applications.